So what I'd like to do in this lecture is take the formula that we found for calculating the arc length of a curve and extend that to a formula for finding the surface area of a solid of revolution, right? So we're back to talking about solids of revolution like we did when we were looking at volumes. So the idea here is I'm going to take this arc and I'm going to rotate it around the x-axis, and that's going to give me a solid, right? And I want to find its surface area. Well, to do that, I'm going to do something very similar to what we've been doing. I'm going to take that interval, I'm going to divide it into n sub-intervals, each one of length delta x, and I'm going to find the surface area of what I get from rotating each of those little individual sub-intervals. Add them up, take the limit as n goes to infinity, it's going to turn into an integral, and there's going to be our result. Well, so I want you to think about what this shape is here. All right, that shape, give or take the sides up here being curved rather than straight, that shape is a frustum of a cone. Right? Remember, to find the frustum of a cone, we start with a cone and we kind of shave off the top of it, and what's left is a frustum. Okay, so ultimately I'm going to add up the surface area of a whole bunch of frustums. So to do that, I'm going to need a formula for the surface area of a frustum. Right, so that's what we're going to spend a little time deriving. And once we've got that formula, the calculus part is going to be pretty straightforward because it should be very similar by now. So to find the surface area of a frustum, I need to start with a cone, right? And finding a formula for a cone's surface area. So how am I going to do that? Well, what do I know here? I know the radius is r, and I know the slant height, and I need my formula to be in terms of those two variables. So what I'm going to do is I'm going to cut down the side of the cone from the top all the way down to the base, right? And I'm going to lay it out flat. And if I do that, I'm going to get a sector of a circle. Right now, what are the pieces of this circle? Well, the outer arc of the circle came from the circular base. Okay, and I know what that length is. It's the circumference of the circle. So this is 2 pi r. And the radius of my circle, that was this cut part here. So that's going to be s. All right, so what I want is I want to find a formula for the area of this sector because that's going to be the same as my triangles, or excuse me, as my cones. So you remember from your geometry or trigonometry class, the angle inside a circle is equal to uh, arc. I don't want to reuse the variables here. Arc length divided by the radius. So for our values here, that means this angle is 2 pi r over s. All right, so that's what I need to get to my area because there's a formula from geometry, right, for the area of a sector of a circle, and that says that the area is 1/2 L squared theta, where L is actually the radius here. So L is going to be S in my diagram, so it's 1/2 S squared. Theta is 2 pi r over S. So we get some the 2's cancel, the s's simplify a little, and the area of my sector here is just pi r s. So that's also the area of my cone. Okay. Now we're ready to talk about a frustum. Right. So I need to label my frustum here. I'm going to put some parts. I'm going to call this R1, this R2, this slant height will be S, and I am going to need this slant height up here. All right, so we'll call that S1. I don't want that to be in my final formula, but I am gonna need it going along the way. All right, so what do I know? Well, the surface area of my frustum is equal to the surface area of the big the big cone. That's going to be pi r1 s plus s1 minus the surface area of the smaller cone. That's pi r2 s1. Okay, now I need to eliminate those s1s, right? So I'm going to rearrange this a little bit. I'm going to make this pi r1s plus pi r1s1 minus pi r2 s1. All right, then I'm going to factor s1 out of here. All right, so this will be pi r1s, that part stays the same, plus pi s1 r1 minus r2. Okay, so how am I going to get rid of that s1? Well, I'm going to do some similar triangles over here. If I draw this altitude, I get two right triangles, right? And those right triangles are similar. So I know that R2 over S1 is equal to R1 over S plus S1. All right, so I'm not actually going to go all the way and solve this for S1, but let's manipulate this a little bit. I'm going to cross multiply here. R1 S1 equals R2 S plus S1. All right, now let's distribute. This is R2S plus R2S1, and let's move that R2S1 over. So R2S equals R1S1 minus R2S1. Hopefully this is starting to look a little bit familiar. Let's factor S1 out of here. S1 R1 minus R2. And you notice over here, I have S1 times R1 minus R2. I'm going to replace that with R2S. Right, so this equals pi R1S plus pi R2S. And if I factor pi s out of here, this is pi s r1 plus r2. Okay, and I'm actually now we've got the formula for the surface area of a frustum, which is awesome. That's what I needed to see. But I am going to make one more little change here. That's going to make things a little easier on the next slide when we actually start to do the calculus bit. I'm going to let R equal the average of those two radii. Right, so then R1 plus R2 is equal to 2R, and that makes my area formula just 2 pi RS. Okay, that's the formula that I need. Now let's talk about this frustum. Okay, so I'm gonna do what we've always done, right? I'm gonna split this interval up into n subintervals, each of length delta x. Right, so if I have one, and I'm going to draw it really big just so I can easily draw stuff on it. Right, if I have a frustum here, right, this was what we're going to rotate to get our frustum. Then what is the surface area of this thing? Right, well, call these points here y1 and y2. Right, and this distance, of course, is delta x. Right, so y1 and y2, those are my two radii. Right, so according to my formula, the surface area of frustum I is equal to 2 pi times y1 plus y2 divided by 2 times the length of this arc. I'm going to borrow geometry notation here. So the length of the arc from y1 to y2. Okay. So what do I know? Well, I know, and I'm playing off of the same derivation that we did for that arc length formula, right? I know that there's a point in here, call it x sub c, right? So that the length of this arc is equal to the square root of 1 plus f prime of x sub c squared. You remember we did that using the mean value theorem, and I bring that up because we're going to have some restrictions on this formula, similar to what we saw with the arc length formula, right? So just kind of keep that in mind, right? Now, what else do we know? Well, look, as delta x gets small, right? Y1 becomes approximately f of x sub c. Those y values start to get really, really close together. And also y2 is approximately f of x sub c, which means that y1 plus y2 divided by 2 is approximately 2f x sub c over 2, which is just f of x sub c. All right, so then the area of my frustum here is now it's going to be approximate now, right? Because I'm no longer using some exact values here, but that's okay. This is 2 pi f of x sub c square root 1 plus f prime x sub c squared delta x. And I should have had that over here, right? This arc length is the square root delta x. Okay, and this is really what we need, right? Then my total surface area is approximately the sum I equals 1 to n, 2 pi fx sub c square root 1 plus f prime x sub c squared delta x. And if I take the limit of this as n goes to infinity, I get that the exact value of the area is the integral from a to b of 2 pi f of x square root of 1 plus f prime of x squared dx. And that's it, right? There's my formula for finding the surface area of a solid of revolution. Okay, so I've cleaned that up here, right? I've got a nice, neat version of the formula. And you notice that we do have some restrictions here, right? This only works if our function is strictly greater than or equal to 0. This is another case where if it drops below the x-axis, we start getting negative function values in our sum, and things can get weird like it did when we were calculating surface areas. So we are going to require that the function has to be strictly greater than or equal to 0. And again, because we relied on the mean value theorem and the formula for arc length, we're also going to require that the derivative has to be continuous. All right, so that's our formula, right? We've got that in our toolbox now. So in the next lectures, we're going to kind of follow the same pattern we followed throughout this chapter and look at some examples of how the formula is used.